Good morning and good afternoon. Welcome to the Splice Machine webinar. My name is Syed Mahmood. I'm the VP of Product Marketing at Splice Machine. I would also like to welcome Monty Zweben. Monty is the CEO and co-founder of Splice Machine. By way of introduction, Monty is a serial entrepreneur who has started a number of companies, including Blue Martini Software, an e-commerce company that he took public. Monty started his career with NASA Ames Research Center as the Deputy Chief of Artificial Intelligence Branch. Welcome to the webinar, Monty.
Thank you, Syed.
Today, we are going to talk about the different approaches of building mission-critical operational applications. To set the context, over the past 40 years or so, SQL has been the primary mechanism of communicating with the backend relational databases, such as DB2, Oracle SQL Server, MySQL, and many others. Thousands of applications have been built using SQL. And then in the early 2000s, a new class of databases began to appear on the IT scene that is known as NoSQL databases, and included products such as Cassandra, Dynamo, and MongoDB. These systems were actually built to deal with the massive amounts of data that they could accommodate, both in terms of semi-structured and unstructured data. So the question that businesses faces today is whether they need to abandon SQL in order to build applications that can deal with the volume and variety of big data. And this is the topic of today's webinar. A couple of housekeeping notes. Please submit your questions through the chat window, which we'll take at the end of the presentation. And we will also provide you with a recording of the webinar to all the registrants. With this, let me turn over the presentation to Monty, who's going to cover the pros and cons of each approach. Monty, the floor is yours.
Thank you very much. Good morning, good afternoon, everybody. I'd love to kind of set the context of today's webinar by just describing why we care about scaling applications and why we care about this comparison of SQL systems versus NoSQL systems. And if you just look at these S-curves, these technology S-curves of looking at the 70s and 80s when we finally were able to automate systems with databases, with systems of record, leading into the 90s with data warehouses where we can really do analytics and derive insights that drive business outcomes, we started to see an increase in the volume of data that's necessary. And of course, entering into the age of the 2000s, with the advent of MapReduce by Google and the open source implementations of some of those techniques in the Hadoop stack, we started to see systems of signals where we're not just storing data from the applications, but storing data from even outside the applications. And then there's a disruptive jump as we see using that data to essentially power machine learning and AI systems, creating new systems of intelligence. And of course, this disruptive, transformative power comes with the need to deal with tremendous amounts of data. And there are inevitable seismic shifts that are happening in the marketplace that increase this demand of this challenge. For example, looking at technological changes in the marketplace, mobile payments is a great example. The amount of transactions generated by mobile payments has exponentially increased the amount of data that needs to be supported by financial communities. And then there are shifts in demand by consumers. For example, in the retail sector and the quick service restaurant sector, the vast increase in fresh ingredients necessary to essentially plan for in the supply chain, knowing that they may spoil, leads to an enormous amount of data that's necessary to, in the moment, be able to track those fresh ingredients. And of course, there is so much buzz about the new wearables that are available from multiple vendors that are generating a new Internet of Things with various sensors. And so with this, we know that this is the new age of intelligent applications. Intelligent applications that can leverage that data from multiple sources at grand scale, use that data to predict what may happen to the enterprise, act upon that, and make those predictions improve over time. And of course, using those predictions, not in some back office, but using those predictions directly in the moment, in the fabric of applications, and being able to deploy these applications on computational resources that are incredibly agile, both in public clouds, private clouds, as well as on premises. And so intelligent applications are clearly emerging in the marketplace. But what's holding companies back? What's holding them back from making all of their applications intelligent applications? And it's clearly architecture. And most importantly, custom applications have been neglected in the marketplace because those were the most important applications that had the most precious behavior that nobody wanted to touch. Nobody wanted to really upheave, but they were the crown jewels for the enterprise that gave them competitive advantage. And they've been largely left alone, creating that real anchor, making it difficult to modernize. So companies have been taking some steps in order to get past that awful situation where they're stuck. And those two steps begin with a cloud migration. And this is a little bit of a misleading move on the part of the marketplace, because while cloud migrations are incredibly important for agility, to be able to grant people the opportunity to use computational resources commensurate to the demand for those resources, it does not change the application that's migrated to the cloud. Those applications don't deliver any more intelligence. They're not intelligent applications simply because the infrastructure changed. So what happens? What happens now is that the companies believe they need to rip and replace those applications to achieve intelligence, and largely seek to do so on scalable data platforms. And in fact, many of these transitions have moved to NoSQL. But there's a real cost to that. The rip and replace of a SQL application to a new architecture is rife with trouble. First, you have to duct tape many different components together. The application itself is going to be migrated in many cases in the marketplace to a NoSQL engine. And then the analytics are performed on a different set of computational engines, often with hours or days of ETL between those. And of course, the introduction of machine learning requires a new set of algorithms to be injected into this, also requiring a great deal of data movement. But let's focus now on the application and modernizing the application to really provide that scale. So why? Why do people jump to NoSQL? What were the reasons for this movement in the marketplace? Well, I think the most popular fallacy is that SQL does not scale, because the data volumes and the velocity of data were increasing exponentially in this new world of seismic shifts and intelligent applications. They thought the SQL systems that were slowing down were holding them back, and they needed to find something new to achieve their goals. But the reality is, it's not the language that was wrong. It was the architecture that implemented the language. Having a centralized SQL relational database management system that held all the data and did all the computation simply could not scale. Whereas NoSQL was a scale-out architecture, sharing data across many servers. But that's an architecture issue, not a language issue. And you'll see in a few minutes, SQL certainly can be scale out as well. The second fallacy that led to the NoSQL movement was schema on read. And this was potentially one of the worst ideas in my humble opinion. And this idea is a very simple idea. Everyone spent in the last 20 years a great deal of time in their application development efforts massaging and designing their schemas for their relational databases, creating a careful structure to the data that was uniform for all users of it and clean and governed. But schema on read is a different idea. Schema on read says, don't worry about what your data looks like. Just grab the data from any source and put it into the repository. And the readers of that data, the users of that data will figure out what's in it and use it appropriately. But this led to 3 major problems. First, along with the schema on read movement was the idea of data lakes, meaning let's just put all of our enterprise data, everything we can get our hands on, into a data lake. And don't worry about it. It'll be easy to access, easy to use, because all the data is there. But because the data was not cleaned and filtered and really made usable, it became a data swamp where the data is in the repository and nobody's using it. The second problem is that if you're not carefully structuring your data, and all the users are structuring the data differently for their use, you may get a tremendous amount of redundant code in your repository and in your applications, just trying to make sense of the raw data that's inside the system. And lastly, if you look at the skill sets of the IT people who are accessing data and providing data, typically the application developer is a little bit different than the database architect. They have different skills and different ideas. And so the database architect is always trying to architect the data schemas and the database for optimal performance. And the application developer is all about building the application behavior. So if you transfer the responsibility of how to access and utilize the data from the database architect to the application developer, you may lose some of that great knowledge available for optimizing that performance. So we think this NoSQL movement was perilous. And we think there's a better way of going about this. Our approach at Splice Machine is to get the advantages of NoSQL, but not to throw away the baby with the bathwater, to keep SQL. Splice Machine's product is an intelligent SQL platform. It is an operational database, just like Oracle or DB2. It's scale out though. The data is not on one server, it's on many servers. And that gives you incredible scalability, elasticity, and performance. But we don't give up the properties that make databases powerful for applications. The ACID properties that preserve the consistency of the data inside of an application are also preserved in Splice Machine. And that's different for a scale-out solution. That's quite unique. But additionally, Splice Machine provides the business intelligence workloads that would normally have been done on data warehouses, separate from the operational workloads. Instead, on the same platform, isolated by different compute engines under the hood, Splice Machine performs massively parallel computations for analytical processing, and it's done in memory. And lastly, instead of moving data from an operational workload to an analytical workload to massage it and put it into an analytical framework, and then perform computation and then exit that data out to a machine learning platform, we've inverted that process and we put the machine learning back in to the database platform where they're unified together on the same platform. So it's an in-database machine learning system. And this can all be deployed wherever you need it, on clouds, on private clouds, or on premises. The architecture, which we won't spend a lot of time on technically, is a scale-out architecture that essentially has the duct tape that I talked about before so pejoratively, but we put the duct tape under the hood so the developer, the application developer, the database architect, the data scientist, and the data engineer don't have to worry about that. On each one of the distributed nodes within Splice Machine, if you connect up from an application through a traditional JDBC, ODBC driver, perhaps load balance to any one of these nodes, a cost-based optimizer uses statistics to optimize plans like a traditional database does, but it does one thing really special. It actually decides whether the query is transactional and operational or analytical, and uses different compute engines, notably HBase, a NoSQL engine under the hood of Splice Machine, and Spark, a distributed in-memory analytics machine or computational engine. And all of this is kept with transactional integrity. So with that architecture, we take customers on a modernization journey that essentially, at the highest level, are 3 steps, has 3 steps. The first step is to take perhaps a very old SQL database and SQL application and migrate it to Splice Machine's intelligent SQL database. Literally 80% or so of that SQL may come over because Splice Machine is full ANSI SQL with many of the kinds of features you expect in a traditional RDBMS, like triggers and secondary indexes and window functions and all the things that you have grown to depend on, all exist. And if there's vendor-specific SQL, we help migrate that over. And then secondly, we unify the data warehouse that existed and add new data on the same platform to provide a unified analytics engine. And then the third step in the journey to an intelligent application is to inject AI and machine learning. This is what is made possible by having a completely integrated intelligent SQL engine that can perform both operational workloads, business intelligence and analytics, as well as having in-database machine learning. So let's talk about the choices people have to reach scalability, the scalability you need for an intelligent application. Well, our thesis is that rewriting to NoSQL is really untenable for the enterprise on the whole. If you look at what has to happen, the first thing is that you have to take the application and all of its business logic and rewrite that application business logic to not use a relational platform, but to use a NoSQL platform. And all of the capabilities, which we'll address in a few minutes, that's in SQL actually has to be written at the application level. And this takes a lot of time, including transactionality and analytical power. And all of the reports that are typically associated with a custom application, written in Tableau or MicroStrategy or something like that, they have to be rewritten to deal with this new data framework. So it takes an enormous amount of time before you can even start to think about machine learning and AI. Whereas with Splice Machine, as I mentioned, many of the SQL queries and the business logic just work on the ANSI SQL Splice Machine provides. And then there's some transition, some stored procedures, if they're in an esoteric language, need to be converted to the programming languages we support. Perhaps there's some syntactic changes that need to be made. But much of our capabilities can just move over quickly including even PL SQL in Oracle applications. And the SQL reports on MicroStrategy Tableau or Power BI or any of the BI tools just work. And so you get to intelligence so much faster. You literally are speeding the time to market for intelligence by many months, if not years, using a much smaller team than an army. It is just simply too expensive, time-consuming, and risky to QA a completely rewritten application. Well, let's dig in a little bit more in the time we have left. SQL is incredibly powerful. This one statement in SQL, using what's called a window function, for example, is something that you just can't do in NoSQL without tons of code. This is essentially a statement that lets you look at multiple rows and reason about multiple rows in partitions. And here you could see we're partitioning by position there, and we're trying to find the previous salary. And so you could see here, the previous first base salary here is $3.6 million. The previous one here is 2.379. And essentially, this is a very declarative SQL statement. You're saying what data you want. You're not saying how you're going to compute it. That's left to the engine to optimize for you. But without full SQL, your code starts to look like this. This is an example of some MongoDB code that forces you to essentially take the light layers of SQL that NoSQL systems are providing and essentially putting them through a sequence in a pipeline of code, not declarative statements about conditions of data, and having to use esoteric MapReduce functionality, for example, to really figure out how to perform an analytical query. And this is just one example of many. And the claim is that your NoSQL leads to a bunch of spaghetti code that does what SQL does for you out of the box, but now that spaghetti is in your app layer for you to maintain for the rest of your life of that application. And moreover, you don't get to leverage all of the work that's been done in 35 years of database research. And so let's take a look at what that means. First, the ability to handle all of SQL's capabilities. And I'm comparing here to Mongo, but this would be largely very similar for the other NoSQL systems. We just picked Mongo as a very popular NoSQL system. The SQL coverage in Mongo is nearly zero. One of the most important things is to have the ability to perform different kinds of joins, and not just different kinds of joins in terms of the SQL layer of inner joins and outer joins, but literally about the underlying implementation of those joins. In SQL systems, there are many different approaches to how to execute complex joins, and optimizers figure out how to pick those joins using prepared statements that allow you to compile out the plan for a particular query and not have to keep processing it. The ability to use semi-structured types, clearly the strength of NoSQL. They nail that. But even in SQL systems like Splice Machine, you can manipulate semi-structured information utilizing all of the native Spark functionality that is inside of Splice Machine and made available in notebooks in a variety of programming languages, tightly coupled to the SQL system. As I mentioned, optimizers are the heart of where 35 years of database research have focused upon, and we get to take advantage of some of the most advanced optimizer technology. And then in terms of query execution, to be able to introspect and figure out which computational system to send something to, analytical or transactional, is simply not available in NoSQL systems. Indexing is, and of course, machine learning is outside the scope of those systems. So I would like to tell a couple of stories before I open it up for questions about how people use an intelligent SQL system like Splice Machine. One story is about a customer service application for a payment company. This payment company had a dispute resolution application that was powered by DB2. And they set out to digitally transform so that the fraud disputes that were brought by consumers and businesses could be reduced from being resolved in 100 days to a month or less. And when they looked at this process, they needed to do two major things. They needed to remove many of the manual processes and make programmatic APIs for merchant banks and for merchants and consumers. And they needed to have years of data reflecting all of the transactions in the world, not just a few months. And I'm really proud to say that today, for this particular payment company, one of the largest credit card companies in the world, has their transactions streaming onto Splice Machine seconds after they happen in the world and forming a multi-petabyte database historically that's available to anybody, merchant, merchant bank, consumer, in milliseconds, and it's consuming billions of these records a day while fielding millions of queries, leading to a much better customer service and hopefully lower and lower fraud loss, and essentially providing an elastic solution. And lastly, another story before I finish is another modernization story off of DB2. A very large European insurance company was looking to modernize their comprehensive insurance system that manages policies, underwriting, pricing, claims, payments, and reinsurance. And these systems were profoundly functional, all running on DB2, 30-year-old application. The company was on a cloud migration journey for a very good reason, for the agility reasons that the cloud provides. They wanted to be able to open up new operating entities in new parts of the world, whether that's emerging markets like Africa or Asia Pac, and be able to bring this particular application live extremely quickly without having to build a data center. In pursuit of that cloud migration, they didn't want vendor lock-in with any cloud provider and was looking for a data platform that could literally field the same queries as that DB2 database. And they chose Splice Machine to do this. But the story doesn't end there. What we also found out was that this particular company had fantastic AI research going on in the lab, performing machine learning on claim data and being able to predict claim fraud quite accurately. But this wasn't live in operation. And the beauty of this implementation is that as they migrate their DB2 application to Splice Machine and have it available both on Azure as well as on AWS, now they can take their Spark-based machine learning models and inject them directly into the real-time fabric of the claim processing, providing in-the-moment fraud detection, AML, anti-money laundering, and prediction of litigation directly in the application that was just transactional over the last 20 years, 30 years. And so that's how I'd like to end and basically say, there's got to be an app in your organization that is experiencing one of these pains. And you don't have to rewrite that app. You can migrate it over to an intelligent SQL platform and quickly be able to resolve some of these pains. Whether they're just performance pains where your applications are slow or can't scale, or to be able to scale, your database licensing is soaring through the roof. Or you're on the journey to intelligence and you're bringing in systems of signals and you need these new data sources and you want to be able to make predictions with machine learning on those data sources in the real-time application. And you need a hybrid cloud strategy, a multi-cloud strategy where you're not locked into one vendor. Or you're just experiencing so much ETL, you need to get out of it. These are the kinds of pains you can look for that we can fix without you having to change or rewrite or rip and replace your entire application. So with that, I'll pause for questions.
Thank you, Monty. That was a great presentation. I would also like to tell our attendees that we have written a blog on this topic, which you can find on our website. The title of the blog is The Perils of Modernizing SQL Apps on NoSQL. So with that, I think it's time to take some of the questions that we have received from the attendees. And I'll start out with the one, Monty, so what are some of the areas that you typically see customers stumble over when they are trying to migrate an application that was originally built on a legacy database to a NoSQL database?
That's a great question, and it really comes down to the complexity that SQL provides, the incredible functionality that SQL provides. So first, there's transactionality. This was probably one of the most important innovations that Splice Machine has brought to market. We've actually patented this, but being able to preserve ACID compliance for transactions where you can commit and roll back and keep your database consistent on extremely, I would say, complicated transactions is very difficult, especially with performance. And I think many NoSQL systems fall behind in ACID compliance, especially in multi-statement ACID compliance, and that ends up with that spaghetti code. Also, the analytical side, it is extremely difficult to figure out how to take a 20-way join query and literally make that work in a NoSQL environment for an analytical behavior that might actually be in an operational system. And that is usually where all of that spaghetti code with loops or MapReduce or these other kinds of systems provide, it turns into a real mess. But those are two good examples of where I think people are extremely challenged with NoSQL, both on analytics and on transactionality.
Okay. Another question that we have received has to do with our Splice Machines architecture. For analytic workloads, do the Splice Machine optimizers replace or augment the native Spark optimizer that the community provides?
Well, that's an excellent question, and it's a complex answer. And so let me see if I can explain it without getting too much into the weeds of our architecture. Splice Machine definitely has a very powerful optimizer. It is a cost-based optimizer that uses an advanced statistics engine originally developed by the open source community. And one of the things I think is important to note that I didn't mention throughout our whole talk today is Splice Machine is open source. And so for all of those in the audience that are open source backers and users, feel free to go to our repository to take a look at the deep functionality within Splice, because we are open source and use open source componentry. The statistics engine we use is open source. That drives a set of optimization rules that actually makes decisions about data access, like which table or index would give me the fastest access to the data in my query. That does not exist in the underlying Spark world. And then the second question is, what is the ordering and what is the appropriate join algorithm? Our optimizer does that, but for certain queries that we find, we might send our query to the Catalyst query optimizer that's inside Spark and let it do its thing. So depending on which compute engine the optimizer is choosing, under the covers, transactional or analytical, HBase or Spark, there may be different optimization technology that's leveraged. Sometimes using our base native optimization search, sometimes using Spark. And I'd love to follow up with the person asking that question at a future time to kind of roll back the detail on that, because it's an intriguing combination and seamless integration.
Great. Another question is, do you think SQL is fading in popularity as the standard for data access and being replaced by popular NoSQL specific language?
Well, clearly I'm religious about that question. I appreciate that question. But I think there's one tell sign that tells us what the status of SQL is, especially if you look over the last 15 years from the beginning of Hadoop and big data to today, including the NoSQL engines in that journey. Every vendor of every data store is adding SQL back into their system. So the bottom line is SQL is clearly the standard, and every database, for the most part, is looking to create a SQL layer so that application developers and analysts can use the language that they know so well. This language is ubiquitous. It may not be the best language ever designed, but it is the one everyone knows. So if you want to leverage the skill sets in your organization, using SQL is extremely cost effective. And I think every engine, including the big cloud vendors, as well as all of the NoSQL engines.
Okay. We'll switch back to the architecture. Do you think semi-structured and unstructured data types should be present in the tables used for operational use cases?
That's a great question too. So there's often a lot of JSON manipulated by IoT applications that are coming directly off of sensors. Perhaps it's JSON coming off of clickstream, things like that. And you have choices in systems like Splice Machine. So if there are extremely large JSON documents or objects that you're going to be storing, it may not make sense to put that in the database. It may make a lot of sense to stream that in, parse it out, create a structured representation of it so that it can be reasoned with inside the database, both for operational workloads that are extremely low latency, as well as analytical workloads. On the other hand, you can actually just store semi-structured information directly into CLOBs and other data types inside of Splice Machine and directly access that data. So there's choices you have in your implementation based on the computational needs, and you get the best of both worlds largely.
Great. We'll conclude with where the market is with regards to SQL. So do you, and application modernization. So do you think most of the low-hanging fruits in terms of apps that can be modernized have already been picked? In other words, have companies typically have already migrated most of the applications where it makes sense to migrate them financially?
Yeah, I think that we're in such early days of this. I had one quote up earlier where Gartner was predicting a tremendous investment in application modernization on the horizon from the next few years. I was recently in one insurance company that told me they have a portfolio of 400 to 500 applications that they're trying to figure out what to do with. These are early days, and some of the early leaders have taken scale out opportunities to reach new capabilities with intelligent applications, and that has been great leadership. But now, in order to be able to do that enterprise-wide for the standard enterprises out there, not the software product enterprises out there, but for companies in the manufacturing segment, the insurance segment, the banking segment, oil and gas and energy, supply chain on the manufacturing and retail side, these companies are not going to be able to do that duct tape that we talked about before, for 400 or 500 applications that need to be modernized, both for scale and for AI. Time is now to be able to use their existing legacy applications that run in SQL or that can be converted to SQL, and their people who know SQL to actually leapfrog all of that duct tape and get a time to market for intelligent applications that the new companies could not afford. They didn't have something like intelligent SQL. They had to duct tape. Now is the opportunity to actually modernize applications and bring them on the journey to become intelligent.
Great. So with that, I would like to conclude our webinar. Monty, thank you so much for your presentation. And I would again like to remind our attendees that you will receive a recording of the presentation in your email. And with that, I would like to go ahead and close the webinar. Thank you very much for your time and have a great day.